So today we'll be studying segment trees. So what are segment trees first of all? Before we start studying any topic, it's really important to understand that what is the utility of it. If I give you two kind of operations, the first operation could be that I'm giving you a range, right, or a set of array or elements, and then I ask you to return me maybe the max of a particular range. So it could be give me the max of the range L comma R or the sum of the range L comma R, the minimum of the range L comma R, the XOR of the range L comma R, or any of such things, right? In that case, you can use segment trees, right? But a lot of these operations, for example, the sum operation can actually be done using prefix sums, right? So let's say I say that given a array, let's say it contains 1, 2, 4, 5, 6, right? I want you to tell me what's the sum of the range of the elements. So this is 1, 0, this is 1, 2, 3, 4. So what's the sum of the elements in the range 2, comma 4, right? If I ask you this, then you can simply say that, okay, what I'm going to do is that I'm going to sum up all these elements. So I'm going to say array of 2 plus array of 3 plus array of 4. That's going to give me the answer. But this would be order of n operation, right, for every query that I'm giving you. So you'll have to sum up each of those elements. So this is a bad time complexity. I don't need it. Now you can say that, okay, in order to improve it, I'll just use a prefix sum. So the prefix sum could be for this particular array, the prefix sum would become 1, 3, 7, 12, then 18, right? And now you can use this. But how? So you can say that, okay, if I need to calculate the sum from A2 to A4, right? Then I'll say the sum is A4, or sorry, prefix of 4. This is the prefix, right? Prefix of 4 minus prefix of the element just before 2. So the element just before 2 is 1, so prefix of 1, right? We can do this. So why do we need the segment tree? Like, segment tree is far more complicated than this simple prefix array. Then why do we need it? Problem is that if I give you this, now you cannot do an update operation over here. Now if I say that, okay, update element at index maybe like 3 and update its value to something like 10, you can definitely update it, but then the problem is that this prefix array would become invalidated. And now if you want to fix this prefix array, then it becomes order of n. So what we understood is that using the very basic operations, you can have the query in order of 1. So query for range, okay, let's say query range in order of 1, right? But then your updation of index becomes the order of n operation, right? And let's say the number of updation operations, if they are order of n, then the total complexity goes up to order of n square, which is something we don't want. We want a very algorithm that can do something better than it. Maybe I am fine with having a query operation even in order of log n, right? And I also want that the update operation is also order of log n, right? So that no matter which kind of queries I'm having, if they are of type 1 or type 2, still my overall complexity, given that I have q queries, so it remains q log n, right? That's where segment tree shines, and that's what we're going to learn today. Any notes so far?
Nope, all good.
All right, cool. So what is a segment tree now? So a segment tree basically is a binary tree, right? So you have a node and it's rooted also. So it's important to note that it's a rooted binary tree. By binary tree, I mean that every node would have either no children or would have two children itself, right? So this is kind of a binary tree. But how does this help? So one of the properties of a segment tree is that all the values of the array are stored in the leaves, right? So let's say our array was a 1, 2, 4, and a 5, right? So using the same logic that all the values are stored in the leaves, this would be a 1, this would be a 2, this would be a 4, this would be a 5, right? That's cool. That's easy to understand. But what's the part? What's the role of other nodes? The other nodes would actually contain whatever operation you want to perform. So since we were talking of sum today, so let's stick to sum. This can be extended to find maybe like the XOR or the max or the min. But for now, let's just stick to sum. So this node, that is this very node which I'm highlighting now, would actually contain the sum of its children, right? So its children is basically 1 and a 2. So it would contain the sum 3, right? 1 plus 2 is 3. This very node would contain the sum of its children, that is 4 and a 5, that would be 9, right? And the top node would also contain the sum of its children or the sum of immediate children, so it would contain the sum 3 plus 9, that is 12. I hope that is pretty much clear. What about the indices now? So this node was actually containing a naught, right? A naught, this was a1, this was a2, this was a3, right? So this particular node was containing the sum from a2 to a3. This particular node was containing the sum from a0 to a2, right? And this node would obviously contain the sum of all the nodes, that is from a0 to a3. But how is this helpful now? Because now if I ask you to give me the sum of any node, you can actually or of any segment. When I say segment, I specifically mean that it has to be a range L to R, right? So you'll say that okay, the sum from a0 to maybe like a2, or maybe like the sum from a1 to a3, or a1 to a2, anything of this sort, right? That can be returned in order of log n. Let's see how to do that. Cool. So what we'll do is, let me just redraw the tree, or let me just cancel these things out. So let's say I ask you that okay, give me the sum from a0 to a2. Fine. Now what you're gonna do is you're gonna start from the very top. You're gonna say that okay, this is the root node, right? So this is gonna contain all the elements from a0 to a3, right? But I'm not interested in all the elements. I just need the sum from a0 to a2. So what do I do? Firstly, so basically it could be in the left children. So there could be three cases. That your sum could be in your left side, the sum could be to your right side, or the sum could be in a combination of left or right, left and right. Cool. So in order to determine if it's in your left or if it's on your right or if it's in a combination of your left and right, what you're gonna do is you're just gonna say that okay, let me calculate the middle, right? So a way to calculate mid would be that the maximum maximum index over here is 3, the minimum is 1, so 3 plus 0 divided by 2, that is 1.5, or if we take a seal, then we can say 2, right? So or I can if we don't take a seal or take a floor, then we can say 1, right? While we are calculating the mid, I would advise not to take seal and floors, and by default C++ actually does a floor for you. So let's say 3 plus 0 divided by 2 gives us 1. So we'll say okay, 1 is the middle, so that would mean that elements from left to mid are in my left children and or in the left subtree, and the elements from mid plus 1 to right are in the right subtree. And over here, left basically is 0 and right basically is 3, because the left limit was 0, the right limit was 3. So this is something that you got to know by calculating the mid itself, right? So once you have calculated the mid, you'll say okay, so the mid is 0, and from this I know that the mid is 1, so a0 to a1 is there in the left, and a2 to a3 is there in the right. Now where do I need to go? So I'll check what the value I need, and the value I need is actually a0 to a1, right? That was what I was looking for, right? So I'll say okay, a0 to a1 is definitely present in the left itself. I don't need to go further because it's only present in the left. It has nothing to do with the right. Now either I could go to the right and return back a 0, or I can stop over here itself, that okay, I'm gonna just go to the left, I'm not gonna go to the right. That's a person preference, or that would depend on the kind of implementation you're gonna do. But in either case, the concept more or less remains the same. So let's say now we go to the left child, and then we say okay, this was a1, I kind of messed it up, yeah, cool. And then we say that I need the sum from a0 to a1, right? Can you give me the sum from a0 to a1 to this particular node? It says that, okay, fine, but first of all, what do you contain? So it says I contain the elements from a0 to a1 itself, right? That would say, okay, so that's a perfect match, right? So over here, the limit you're checking for, or your L comma R, is actually 0 and 1, and the node itself, right? The node itself contains the elements from, so let's call it TL or tree left. Tree left over here is 0, and your TR or tree right here is 1, right? So your left is less than equal to tree left, and your right is greater than equal to tree right. Cool. That basically means whatever you're looking for, right? If you're looking for this particular range, and this particular range is entire, your particular subtree is entirely in that range, right? Your particular subtree is TL to TR, and this itself is completely in the range L to R. Cool. So from this node, you can say that, okay, whatever value I have stored at this particular node, I can return that, right? So it will return 3 to this, and this will throw back 3 to you. So in the end, you'll have your answer as 3. That was your sum from A0 to A1. Is this cool? This was a very base case, but is this clear?
This is just one case where the answer is either in the left or in the right, right?
Right. So I'm gonna explain the case wherein the answer can be in the left and as well as in the right, but I just wanted to know if
Yep, yep.
anything's going, a bit hard, or if you're unable to understand anything. So you can just let me know. Is anything
Yes.
everything clear, guys?
Yep.
Okay, cool. Now let's erase all of it. But we want to do some more complicated stuff, right? So like he said that, okay, this was a very base case wherein like the thing was either present in the left or present in the right, but thing could get a bit weird also, or a bit hard, and you can actually get queries wherein the things are to your left as well as to your right. For example, now if I ask you that, okay, enough of easy queries, now give me the sum from maybe like a0 to a2, right? So how would you do that? Again, the same operations would follow. Let me clean the screen a bit. Okay, a bit more maybe. Okay, fair enough. Okay, now the same operations would follow. You'll go to your go to your node. You'll say that, okay, what's your mid? The mid would be 3 plus 0 divided by 1 divided by 2. That is 1, right? So that tells you that, okay, 0 to 1 is present in the left child, and 2 to 3 is present in the right child. And what do you need? You need 0 to 2, right? So that basically means there's an intersection between the left child as well as the right child, because because 2 is present in the right child, whereas 0 and 1 is present in the left child, right? So we'll have to process both the scenarios. For now, let's proceed as normal. So let's say firstly we go to the left child, and then we'll go to the right child as well. But right now we go to the left child. We say our left is 0, right is 2, right? And the tree left for the left child is 0, right, over here. And the tree right for the right child is 1. Cool. And the tree right for the right child is 1. Again, what happens is that your left is less than equal to TL and your right is greater than equal to TR. So we know that this entire subtree, so when I say entire subtree, I mean this entire subtree is a part of the query you are asking for. So you'll say that, okay, since it's already a part, I'll return the actual value. So it will return 3. Now this part is computed, so the left part is computed, but you have to compute the right part now. So you'll say that fair enough, but what about the right part? So we are going to go to the right as well. Now we are going to say, let me just clear it again. So now you're going to go to the right part. You're going to say what's your left? Left is 0, right is 3, sorry, right is 2, and your TL is okay, 3 left over here for this is 2, 2, 3, right? So TL is 2, TR is 3. So basically, like the very base case we were checking, wherein like the entire subtree is a part of it, doesn't hold. So we have to go further down, right? So even at this particular node, we'll calculate what's your mid. So your mid would be 2 plus 3 divided by 2, that is 5 divided by 2, that again would be 2, right? So this would tell you that, okay, the left tree would contain TL comma mid, that is 2 comma 2, and your right subtree would contain 2 comma 3. sorry, 3 comma 3, right? So now 3 comma 3 is not something you're interested in. You're just going to focus over here. So from this node right over here, you're going to go over here. You're going to say that, okay, you're going to again perform the same operation, that what's your TL, what is your TR. Now over here, the values would actually change, like the L and R. Okay, the L and R are going to remain the same, but these values are going to change, right? So you're going to say the TL now is 2, right? And the TR now is 2. Now the condition that your TL is greater than equal to your L is less than equal to TL and your R is greater than equal to TR, now it holds, right? Because 0 is less than equal to 2 and 2 is greater than equal to 2. So this condition holds, and hence it can say that my entire subtree, now it's a bit stupid to say entire subtree because it's a single value actually, but that's the very concept. Like when we code things up, we try to keep the things generic. So for simplicity, we are going to say that the entire subtree actually contains the value we are looking for. So it's going to say that, okay, my value is fine, I'm going to return a 4, right? So it's going to return a 4, and over here this is going to return a 4 back, and a node would then combine the results it's getting from the two children. And since over here we were talking of sum, so it's going to say 3 plus 4, and it's going to return us a 7. Clear, guys?
Yep.
For the remaining people. All right. Yep, that's pretty much cool. Yeah, so that is all that is regarding segment trees. Now I don't know why it's hyped up that much that it's tough or so. It's actually very easy concept to understand. Like if you understand the very basics, then it's very easy. But wait, that is only one part of the story, right? There was another operation that we had to perform. That was that you have to update a particular element. Now how would we do it? Now when we are talking of the standard segment tree and not the lazy segment tree, right, then we are specifically talking of a point update. So we are going to just update a single value at a time. So let's say I give you the task that, okay, update location 1 with a new value, maybe 10, right? So using the same approach, firstly you will go to the root, and over here you will check what's your mid based on the value of mid. So firstly you will check the mid, right? Based on the value of the mid, you can see that either I have to go to the left child or to the right child, right? Then you'll start traversing your child, and at the end you'll eventually come to a leaf node which contains that particular index, right? So after doing it, you'll reach over here, you'll update its value from 2 to 10, but then your segment tree becomes invalid, right? Because now this value is wrong, and also this value is wrong. Not this part, yeah, this value is wrong. So what you're going to do is on your traversal back, like you are performing a depth first search, right? Or you're performing a DFS traversal. On a traversal back, you're going to update the values. So over here, you're going to say that the value is equal to the sum of its children. That would give it a value 11. So the value changes from 3 to 11. On its way back, you want to say that, okay, the values over here is also going to change. So its value would become the sum of its children. That is 11 plus 9, that is 20, right? Uh, just to be extra safe, let's just calculate the sum of the elements. So this is 1, 1 plus 10 is 11, 11 plus 4 is 15, 15 plus 5 is 20. That is correct value at the root. And also over here, we updated the value is 11. Let's just calculate that also. So it has two children, that is 1 and 10. So it also is having the value 11. So that's perfectly fine. And yeah, that's pretty much segment tree, or the standard segment tree. Any doubt in this? Now the thing is that whenever you encounter such problems, maybe on AtCoder, on LeetCode, or on GFG, then yeah, this standard implementation would definitely help you, and you can just even copy the code, make some modifications, and use it. However, on platforms like Codeforces, which rely heavily on constructive algorithms, you might have to tweak it. You might have to understand more in detail and stuff. So I'll say I'm definitely going to give you some time. You can understand the things in detail in this entire time period, and then you can you can start solving harder problems. Cool. So today I'll try to solve a CSES problem that is somewhat similar to what we already did. So this is dynamic range sum queries. The problem states that given an array of n integer, your task is to process key queries of the following types. So type 1 operation is update the value at the position k to u. Type 2 operation is what is the sum of the values in the range a to b, and the first input line has to integer n and q, blah blah blah, basically the standard shit. But anyway, the thing is, over here, if you check the constraints, right? So the constraint is n and q can go up to 2 into 10 to the power 5. Now, if I use a standard a very basic data structure, or if I just try to brute force it up, then the time complexity would become 4 into 10 to the power 10, and that would obviously give me a TLE, right? So I have to do something that can reduce the time complexity, and obviously segmenting can help us over here, because this is almost the exact thing we discussed right now. So I think this would be a good example to even teach the implementation as well. So this is the code. I didn't like, I do have my own implementation, but I didn't copy it from that. I coded it from scratch so that I can also teach you how things are working. So this is my segment tree. Don't worry about the length of it. It looks a bit long, but it's pretty simple to understand. Firstly, let's have a black box view. Like, let's say you just copy paste this code. So would you be able to work with it, right? So let's try to understand in that respect. So firstly, I am taking the values n and m, or you can say n and q. Let's change those values names to n and q over here as well. Cool. So number of elements, number of queries, then I initialize the vector, and then I take in the vector. Once I've taken the vector, then I instantiate the object for the segment tree, and I pass my vector into it so that it can start building it, right? Now, how the building operation is done, I'm gonna come to that, but right now just focus on the black box view. Then if it's a type 1 operation, that basically means you have to update the value. So you take the value, you take the index, the value, you decrease -1 from it because we are taking zero-based indexing, and then you update the value in the segment tree. How it's doing that, we'll come to that later. Or if it's a range query operation, we take the range, obviously -1 from each because it's zero-based indexing, and then we print out the range. So yeah, that's pretty much it. The benefit is, if you are having very standard problems and if you have the code, this code, you don't even need to do anything. You just need to copy paste this entire thing, right? And all you need to know is that how do you even use the update operation, or how you use the get value operation. That's all you need to know, right? Now let's try to understand how it works. So let's start from the very beginning. So once you pass the vector into the constructor, it firstly takes the size n, right? And n would be obviously the size of the array. One key thing about segment tree is that over here you observe that you were having 4 nodes in total, right? But the size of the segment tree was 4 plus 2 is 6 and 1 is 7, right? So for 4 nodes, it's 4 nodes or 4 indices. You actually required a segment tree of 7 nodes, right? So the number of because the indices or the actual values are only getting stored in the leaf, so the entire rest of the structure also needs its space. Now there's a very precise estimation for it, but in order to make the things a bit simple, we try to estimate it. So we say that the size of the segment tree size is 4 into the number of values we are going to store. Now if you want to study more about it, you can Google it up, you'll find the exact proof. But yeah, this is something I just want you to know, that the size of the segment tree is estimated to be 4 into the number of indices you are trying to store in it. So over here we are doing the exact thing. Here's the code. Yeah, over here we are saying that the tree size is initialized to 4 into n, and initially all the values are 0. That's fine, and then we'll start building the tree. But wait, now we are storing the entire tree in an array, right? So we are storing the entire tree in an array. But the problem is, array only has indices 0, 1, 2, 3, 4, 5, 6. It doesn't have nodes, right? So how do we know what's its left, what's its right, etc.? So we make another claim over here that for any node, let's say its index is idx, then its left child would be idx into 2, and its right child would be idx into 2 plus 1. So if I have a very standard implementation, so let's say this is 1, and this would be 1 into 2 1 into 2, this would be 1 into 2 plus 1, that is 3, this would be 2 into 2, that is 4, this would be 2 into 2 plus 1, that is 5, this would be 3 into 2, that is 6, this would be 3 into 2 plus 1, that is 7. Similarly, this would be 5 into 2 that is 10. This would be 5 into 2 plus 1, that is 11, right? So these are basically the indices. So we can then map them onto array. So this node would come over here, this node would come over here, and the 0th node is obviously wasted, let it be. And this node would come over here, this node would come over here, right? This is 3, this is 4 would, okay, this is 5 would come over here, 6 would come over here, so on and so forth. Is this part clear? Because there's nothing more left to segmentary, then I can start coding up things. Any doubts?
Nope.
Okay, good enough. Okay, so yeah, we say that our size has to be like 4 into n, and then we start building the tree. How do we build it? Firstly, we check a case that is stupid enough, that is your left is greater than your right. That can't happen, right? If that's happening, then we just return it. If your L is equal to R, that means we are talking of a single index, right? Because there's no range, there's a single index. And that means we have reached a leaf node. So we say that the value of the node is equal to the value of the array, right? So tree of node is equal to value of this L or R. You can use any of these over here because technically both of them are same. Else we calculate the mid. Now mid is equal to L plus R divided by 2. Over here, you need to make sure that when I'm saying L and R, I'm basically referring to the ranges we had defined earlier. So basically when we are calling L and R over here, that I had talked about earlier, this is 0 to 1 or 2 to 3, or this was 0 to 3, right? These ranges which we had defined earlier are being talked of when I'm saying L and R, right? Cool. So mid is L plus R divided by 2. Then I'll say I'll build my left subtree, I'll build my right subtree. I don't care how they're getting built because this is the recursive function that is going to be called again and again. And the very basics of recursion is that you focus on the current problem and delegate it further to your children, right? So you're going to say that, okay, build my left subtree, build my right subtree using the same function. Also, when you are done with the DFS, you have to combine the answer, right? So you are going to say that your tree node is equal to whatever value was there in the left node plus whatever value was there in your right node. Cool. Had it been a different thing, for example, XOR or maybe like max, min, then operation would have changed. For example, for max, you would have taken max of left node and max of right node. Or for min, you would have taken min of either of these two nodes. Cool. Cool. So that's how we are building it. Any doubts in the build function? I think it's good enough. But okay, cool. Let's proceed further. Let's proceed to get value. Now, what's get value? So I'm just giving you a quick tip over here. Whenever you're coding, maybe in development or in CP or any other place, whenever you're gonna call a method from outside the class, keep it as simple as possible, right? It shouldn't contain extra details. It should contain only those details that the user might want to put in. So as a user, when I call the get value function, I expect to give it two values. That is what is my range, that is defined by L and R, and it should return me the answer, right? So it's only having two values, L and R. But when I'm calling the function, it requires a lot more details, right? It needs to know what is the node of the like what is the index of the node, what is the range of that particular node. That all I'll fill up over here, right? So this is the internal implementation for the same function, right? I'm gonna call it from this function itself. So over here, I'm gonna tell it that okay, I want the sum. I want the sum for the range L to R. But now, where do I start? So I start at the root node, right? For the root node, the index is 1. And what elements does the root node contain? So it contains all the elements from 0 to n minus 1, right? So that's what I'm telling it. So I'm calling it with the ranges, that is LR. I'm telling it that the left element it contains, or the left range of it, starts at 3 left, that is a 0. The right range ends at n minus 1, that is 3 right. And the index of this node or the node itself is 1, right? And once we start the very basic check that if your tree left right is less than tree left, that means an invalid scenario, return a 0. But if your entire subtree is a part of the range you are querying for, that means that if your tree left is greater than equal to L and your tree right is less than equal to R, in that case your entire subtree is a part of the range you are querying for. So return the answer, whatever is there in that particular node, right? If that's not the case, so there could be another cases that could arise over here. For example, the range you are like you are standing at a particular node. So this is this particular example. Like let's say you wanted the sum for a naught to a1, right? Or let's say you just wanted the sum for a naught, right? So checking the sum for a naught, if you are standing at this particular node, then this is stupid enough, right? Because you are standing at a node a2 to a3 that contains the node for a2 to a3, and you are specifically looking for a naught, right? So a naught is actually the left less than the left limit for it, right? So this is stupid enough, and it's not going to return you anything useful. So you can just return 0 from this node, right? So if your left tree left is greater than right, or your tree right is less than left, in that case it doesn't contain anything meaningful. So just return a 0. But right now, if you are just talking of a single index, now all of these like all of these things didn't hold. That would basically mean that you are actually standing at a single point, right? You are standing at a leaf node, and this leaf node would definitely be a part of your answer. So if this is happening, that basically means you are at a leaf node, right? If you are at a leaf node, you can just return the answer, it's correct. Else you'll say that, okay, I need to get the sum from my children, so let's calculate mid as tree left plus tree right divided by 2. Then you go to the left. For left, you say that, okay, the range is going to remain the same. I want to query for this range. Tree left would remain the same because we are talking of the left children, of the left child. But the tree right would now be limited up to mid. And the node's value is obviously node into 2. Plus the right child. The right child would also be having the same range. But the left range for the right child is mid plus 1. The right range for the right child is tree right. And the node's value is 2 into node into 2 plus 1. Yeah, that's pretty much it. Also what so yeah, this is the second last operation, and after this only one operation remains. Any doubts?
In the build function, did we do one based indexing? Like here, you took node equals to 1, right? For get value.
Yeah. Okay, so okay,
Yeah.
I got a point. So basically, when you're talking of the tree, right? So when we're talking of this tree array, in order
Mm.
to ease up the thing, because we are also assigning it a length of 4 into n, right?
Yep.
So when we are talking of the tree array, we specifically talk of one base indexing, right? So tree array
Okay.
in particular contains one base indexing, but when we are talking of the ranges that it's going to contain, those are all in zero base indexing. You could change that as well. The only problem is that it gets sometimes complicated, because sometimes the problem provides you the indices in zero base, right? And then you have to make all the changes over here. So for simplicity, what we generally do is that the tree actually contains one base indexing. The benefit is because if you remember, then over here we made a formula, right? That your left child would be indexed into 2 and your right child would be indexed into 2 plus 1, right?
Gotcha.
So
Gotcha.
if we start from
Into 2
0,
function.
so this would also become 0, right? Because 0
Gotcha.
into 2 is actually 0.
Yep. Yep.
So yeah, this would actually not follow. So that becomes a problem.
Hmm. Gotcha.
And that's why we start the tree array specifically from 0 base indexing. Got it?
One base. Yeah. Sure.
Sorry, 1 base, yeah. Cool. Yeah, any other doubts? If you take 0 base, then yeah, if you take 0 base, then obviously you can do this. Cool. So what about the update function? Now the update function, as I said, would only be considering a single value. It would like to update the value at the index idx to a new value, right? So, and these are the only two parameters which the client or the consumer might be constructed in. So let's keep it till that only. So for this index, I need to set the value to new value, and internally I can populate more values that I need. So I'd say that, okay, I'm gonna call it for the root node. So the root node has the left limit as 0, right limit as n minus 1, and its index is 1, right? And the same things would follow now. This is the stupid case wherein your range doesn't even include that point, so return. But if you are at a leaf node, that would mean that you are at the right leaf node, so update the value, right? Else take a mid. Similarly, perform the update operations, like for the left child, for the right child. This is almost, or you can say almost exactly same as this one, right? And this is exactly same as this one. So basically the operations are somewhat similar in all the functions, right? After that, you have to update the values, right? as I said that you are performing a DFS, so when you are coming back, just keep updating the values on the nodes. So that is what you're doing over here. And if I run it, then yeah, it passes. That's pretty much segment tree for you. Okay, bro, you're right. Actually, I do have defined statements over here. So my int actually means long long. Cool. And yeah, one more thing. You might it get a weird feeling like I'm just directly taking in the vector, right? I'm just like inputting the vector itself. That is because I have pre-written codes, or I have all these statements that help me take the entire vector as an input at once. If you directly try to take in the input like this, your code would fail. So one thing you can do is you can copy my code. I'll provide you snippets, and then you can do all of these things. Okay, cool. Yeah. So one thing is that this specifically is a segmentary that works on sums, right? Now I might give you another operation that, okay, give me the max of each node, right? So what you're gonna do over there is that you're probably gonna do a max over here, right? Let me just say, rather than doing it, max over here, a max over here, a max over here, right? And that would actually work. And also you'll have to mm, uh, take care of the other values. For example, when you are returning the values, if you're talking of max, right? So you have to return int min then, right? So that if you have having negative values, it doesn't affect those. So all of those changes might be required. So another thing you can do in order to improve it is use a function maybe like void combine, right? And pass it the node. What it's supposed to do is that whenever you use combine, its internal implementation would be that tree of node is going to be tree of node into 2 plus tree of node into plus 1, right? Now how is this beneficial? I can use this combine operation over here, right? So I can just say combine node, right? And similarly over here I can just say combine node, right? But how is this beneficial? The benefit is that it could be the case that you are using some more modification of a segment tree, and then these combine operation are being used multiple number at multiple places. So whenever you need to change it, right? So just take for instance, I'm going to copy paste this code for some other problem, right? And now I need a different kind of a implementation for combine, right? So I just have to make one change over here rather than making changes at every place. So I can say that this is going to be max of left comma right, or I can do a XOR, or I can do whatever I want over here, and I add one more place that is over here, right? So I only have to make two changes. But in the previous implementation, you would have required to make like n number of changes depending on how many places you have utilized that particular operation. So this at time becomes helpful. And that's pretty much it. Let's just test that we didn't break anything. Let's just try to run it again. Yep, it still works, and I'm not going to submit it again, but I had already submitted the same code earlier. This is the exact same code, and this works. Now, what I expect you guys to do is that just try the simple problems for segment trees. In a couple of days, I'm gonna take another session that would be on lazy segment trees. And I'll try to use this particular template as much as possible so that it's easy for you guys to understand lazy segment tree as well. Now, lazy segment tree is kind of an important topic. Yeah, I saw lazy segment tree a couple of times in the past couple of months, I'll say. I saw it yesterday in the at coder F problem. That was a very interesting problem, and it required lazy segment tree and a very very basic implementation of it. Nothing too fancy. Basically, the sum itself, the max and sum itself. So I'll teach that to you guys, but I do expect that you master segment trees before that particular lecture. That's gonna happen in a couple of days. But if you still have any sorts of doubts in this implementation or anything that is related to segment trees, please let me know.